All right, this chapter is lesson 3.2, linear functions. So you need to be writing the vocab in your journals. Okay, so when we're identifying linear functions, that's just a fancy way to talk about a line on a graph, linear functions. So when you hear a linear function, what picture do you think should come into your brain?
A line.
A picture of a line on a graph. So a linear function is going to create a line. So anytime you hear that phrase, it's a line on a graph. It's always going to be able to be identified by slope-intercept form. You should have seen a little bit of this in 7th grade. Y equals mx plus b is the equation. If you haven't written that in your journal, write it right now. I'm going to write it on the board with some extra stuff on it because this is probably the most important equation you will learn this year.
So this will go under linear equation?
Yeah, that's fine. All right. I want you to write everything I write on here in your journal. So y equals mx plus b. We're going to talk about what each of these letters is representing. So m, what do you think m represents? Nope.
Meters.
Nope. All good guesses. So m is always going to, represent your slope. So when you write this equation, when there's a number there where the letter m is currently, that represents the slope of your line, whether it's going up by 2, over by 1, down by 2, over by 3, whatever. This represents your slope. B,
base.
These are good guesses, but no. This is your y-intercept. No. They're just random. B is your y-intercept. So y-intercept. Does anybody know what a y-intercept is?
Where it gets intercepted.
With the y.
With the y-axis.
With the y-axis. So if I draw a graph here.
Oh, when it hits the y line?
Correct. This is my y line, right? This one, the up and down one. This is my x line. So going across here are all the possible points. Going across here, all the possible points. When I draw a line, wherever it crosses, that's a super straight line, I'm sure. Yep. This point where it crosses my y line, this is your y-intercept. Because it intercepts the y line.
Oh.
Okay? This would be my x-intercept. We're not going to do that right now, but wherever it crosses the x line is your x-intercept. Make sense? Okay, the x and y that are represented up here, these are a point on the line. So the x and y here are any point along this line. If I were to have the x-intercept, let's just pretend I had the x-intercept, I could plug the x-intercept right here where the x is and plug in what I know about any other letter and solve it to know what the y is, the y value of that point is. So if you're just missing one variable, you can solve for it, right? You just rearrange and do the math. This is what I want to see in your journals. This is probably the most important thing you're going to learn this year. So we're going to do a lot of it. Okay? There's a couple other variations of solving for slope, solving for linear equations that we'll do when we talk about systems of linear equations.
Okay, but I have a question. What's a slope?
Slope. So the slope is just talking about the angle that your line is. So like a slope of a hill, same thing. So if this is a hill, I'm going up, over, at this rate of change.
Right.
So when you use this in real life, that's a great question. When you use this in real life problems, the rate of change is your slope. So if we talk about money, how much money I'm making per job per day, that's your slope because that's the rate of change. Okay, if I'm talking about how fast I'm walking, how many steps I take per minute, that's your rate of change. That's your slope. Excellent questions. All right, so let's look at example 1. It's very quick and easy on these ones. So we're going to identify linear and nonlinear functions. So what's the word linear tell you?
Line.
Should be a line. So let's look at graph A.
No.
Do we have a line?
No. Yeah.
No.
No. We have a parabola. You'll learn about that later. So this graph is not a line. So this is not a linear function. Non-linear.
Non-linear.
Yeah, however you need to spell it.
No.
No. So B, does this graph represent linear or non-linear?
Linear. Yes.
You can't say yes.
Yes, linear.
It's asking an either or question.
Yes. Linear.
This is a linear
When we ask my dad
equation.
every question, he says yes.
Yep.
A or B, D.
42. All right, super simple, right?
Yeah.
So I'm assuming your try-its are going to be about the same. Not your try-its, monitoring progress, whatever grade this is. All right. Oh, we got another example. Just kidding. Example 2. I lied.
That's not good.
I know. Shame on me. All right. So we're going to look at a table and decide if it represents a linear or nonlinear function. So what did we learn about tables on the last lesson? On functions. Yep. Hold on. Go ahead, Charlie.
An input cannot have more than one output. But
Correct.
An output can have more than one input.
Correct. So let's look at these tables and decide if the input output is correct. So on A, we have 3, 6, 9, 12, and each one of these have a separate output, correct? Do you think that forms a line?
Yes,
It would.
Maybe. Just because it's a constant rate for both.
Correct, because it's a constant rate of change, aka slope, for both. It goes up by 3 and down by 6.
Yeah. That makes
Over by 3, down by 6. So then, yes, this is a constant rate of change, so this function is linear. We didn't even have to graph it.
Oh, wait, no.
Wait, do we have to graph it in our notebook?
Not unless it specifically tells you to graph.
Are we
The
gonna
only
graph
time you have to graph for me is if it specifically says graph this equation. And actually, I changed that rule when we do the equation linear systems where you do substitution, because that's my favorite math. And so I make you do a lot of it. It'll help you in high school, I promise. All right. So let's look at the second one. It goes up 1 to 3, 3 to 5, 5 to 7. Is that a constant rate?
No.
Yeah.
Yeah.
Up by 2.
Yeah.
Then it goes 2, and then 9, and then 20, and then 35. That's awkward. So what that graph is doing, it's a squiggle.
No.
So the rate is not constant, which means
Non-linear.
nonlinear. I know you want to write no and yes, but it's asking a question specific. All right. Now are you doing monitoring? There you go. 4 questions. Go do them. Shouldn't take you very long. Okay, this is example 3. I did. I did.
Laggy.
Yeah, it's been very laggy.
It's going. I'm here. They can hear me. So which of the following equations represent linear functions? So we're going to look at each of these equations and decide which one is a line. My face pauses. It's okay. I think it's just because it doesn't pause on my computer. I think it's just the projection.
Okay.
So I think if I'm laggy online, I'm sorry. All right. So let's discuss each of these. Y equals 3.8. Does that match our slope-intercept form up here behind my head?
No.
Why not?
It doesn't have all the stuff.
It doesn't have M plus B.
This is the M. Actually, this is the B. There is no slope.
Yeah, where's the slope?
There isn't a slope.
And there's no X.
That's the slope. Yeah, there's no slope. There's no mx in this equation. Do you guys know what it means when it just says y equals 3.8?
A singular point on the.
You're right. So it's a
Not a line, it's just a
horizontal line across that x or the y-axis.
Wait.
They'll always be horizontal, not vertical.
So your slope is technically 0. Yeah, because it's the y line. So it's ploop.
So the slope would be 0, right?
So the slope would be 0. So is that a constant slope?
Yes.
Yeah, sure it is. It's always 0. So this is probably a horizontal line.
so it's
Yes, it represents the linear function.
Yep. What about this one?
No.
No. That's going to give you some kind of crazy. What about this one? 3 to the power of x.
Yeah.
No.
That's not a constant rate of change. Okay, 2 over x.
Maybe.
because you could have x over a number because you could switch that into a fraction next to the x, but a number over x, that's going to give you a funky graph. Can we simplify this into y equals mx plus b? Yeah, you can distribute this 6, right? 6x minus 6. That's a slope. That's a constant rate of change, so this would definitely be 1. This one we have x squared. So that's going to be a different. Okay. So the only ones you can have are the first one. We talked about that one. That's going to be a horizontal line. And then the very second to last one, the y equals 6x minus 1. So those are the only 2 linear equations out of this whole thing. So when you're looking at all these funky equations, all you need to try and do is write them in slope-intercept form. This equation, y equals mx plus b behind my head. If you cannot rearrange it to mirror that, then it's not a linear function. Okay? Questions?
I don't know what to ask.
Yeah.
How do we determine whether an equation is a linear function?
If it,
Slope-intercept form. That should be your answer. Slope-intercept form. All right. So, do we do another example? Nope. Monitoring progress. All right, let me look at these with you. Just because they might be more difficult. That one's not difficult. Y'all should be able to do that one. All right, so real quick, look at number 6.
number 6? Oh.
Or number 2
Number 2.
on you guys. So this is 3x over 5. Could I write this as y equals 3/5 times x?
Yes.
Yes, you can. So then this one would be a linear function because of those reasons.
Because it has constant change.
Yes, constant rate of change.
Yes.
And then this last one, we have x squared.
No,
You can't ever have an exponent on the x.
you can never have an x squared. Never have an x.
Yes, you can rearrange.
I didn't. I don't know.
All right, I'll give you a minute to finish that.
Rock.
All right, so identifying linear functions. So an output is 3 more than the input. So this is the phrase they want you to write into a linear function. An output is 3 more than the input. What is our output value? Our domain and range? Y. Y is the output. X is the input. We learned that last lesson.
Yeah.
So it's telling you an output is 3 more than the input. So you take the input value, which is x, input variable, and we add 3 to it. And that's what equals y. Here's the equation that you get. Do I need to say it again?
No, yes. It makes sense.
The output, y, is equals 3 more than the input.
Is that always like that?
It's always that simple. I mean, they'll get more complicated sentences, but yeah.
But is it always 3 more than the input?
No. This is just showing you how to write an equation with a phrase. It's just showing you the different ways you can represent the function. So the first one is in words. The second one is by the equation. The third one is creating an input-output table.
But those are easy.
These are easy. You get to pick the x values because those are your input values.
Yep.
Plug them in for x, and they give you your output values. Everybody just remember those. Once you've done an input-output table, you can create a mapping diagram. The input -1 created the output of 2. The input of 0 created the 3.
Do we have to?
Not very often. I might make you do it once, and once you got it, we're done. And then once you have these points, you can graph them on a line. So you have -1, 2, 0, 3, 1, 4, and 2, 5 on this line. Now, when you're graphing, if you know that these are constant rates of change, which you would because you can see the equation, you don't have to graph all 4. I would just graph 2 dots and draw a line. Because it's a constant rate of change, we can see it here in the equation. There's no need to graph all 4 dots. You can just do 2 of them, and then you know where it's going to go, and you just draw the line. All right? Questions? Excellent.
That was not an example, right?
No, that was just information. All right, graphing linear functions. So a solution of a linear equation in two variables is always going to be an ordered pair. So if I ask you to tell me a solution, Charlie, focus. She was just zoned out. If I ask you to give me a solution to a linear equation, you're going to give me the answer in x, y in a pair, in an ordered pair. Everybody know what an ordered pair is? Yes.
Yes.
X comma y. And that point is a solution to your line. It means it's on that line if I were to graph it. Discrete domain, here's you're going to get discrete and continuous domains, and they really kind of apply towards real life situation. Discrete is a set of input values that consists of only certain numbers in an interval. So they're whole numbers, 1, 2, 3, 4, etc. I can't use discrete. Well, let me talk about continuous. A continuous domain is a set of input values that's anything within that range from 1 to 5. So, for instance, if I have a continuous domain, it's like eating, a continuous domain would be like water filling up a jug. Can I have part of the whole number filled up with water? Yes. If I was talking about the number of granola bars that I wanted to feed my class, can you have half a granola bar? I mean, you can, but that's when they're asking you to divide by so everybody gets one granola bar. That would be a discrete because you want to make sure that everybody gets a whole part. You'll hear, these are kind of weak examples. If you're counting cats in the neighborhood, can you have part of a cat?
No.
Please no. Okay, so that's when you think about discrete or continuous. Continuous means you can have a part of a whole, whereas, did I say discrete? I meant continuous. Continuous, you can have part of a whole. Discrete is whole numbers only. Comprende? All right, example 4. This one is a little bit of a long example. Yes, you do need to write it in your journals. So we have a linear function. Y equals 15.95x. This represents the cost of dollars, which is Y, of X number of tickets for a museum. Each customer can buy a maximum of 4 tickets. So we're going to find the domain of the function, decide if it's discrete or continuous, and then we're going to graph it. So it is a long process here. All right, so first, can you buy a part of a ticket? No. So if I can't buy a part of a ticket, are we discrete or domain? Or continuous? Discrete, because you can't buy a portion of it. So discrete is correct. Because X represents the number of tickets, it must be a whole number. The maximum number of tickets is how many? 4. All right, so we know the possible number of tickets for our X values is 1, 2, 3, or 4. So do we have our input values?
Yes.
Yeah. We have our domain?
Yes.
Yes. Now, because we have our domain, can we find our range? Yes, we plug in these 4 numbers for X, and it will help us solve for Y. Do you mean to go back? That's fine. So right now, this is, we make sure you've written this equation up there, because that's what we're dealing with.
So that would be the linear equation, right?
Yeah, Y equals 15.95x. That's the linear equation. And then you need to write domain equals 0, 1, 2, 3, or 4, and that we know it's discrete.
Oh, wait. Write the table?
We're going to. We haven't got there yet.
Yeah,
All right, so we're going to graph this function using its domain. So you're going to make an input-output table. I don't mind if you make the simplified version of this one, where you have the equation up at the top, and then you plug in all of the x's, and then you get your y's. That's fine with me. So you'll plug in these 5 possible 0 tickets, 1 ticket, 2 ticket, 3 ticket, 4 ticket. And obviously 0 times $15.95 is 0. If they buy 1 ticket at $15.95, the cost is 15. No, they bought 1 ticket. $15.95. They bought 2 tickets.
So all of this was just to figure out if you got how many tickets they got.
And what their cost would be.
That's so sad.
Well, they're giving you a simple equation, because if they gave you a super complicated equation, y'all would freak out. We start with simple, and then later on we make it more complicated. We'll stop. You got this.
Now I'm freaking out for later.
That's fine too.
That's like
Understandable.
it's
So then your x and y value is your x point and then your y point that you solved for. So the first one's easy, 0, 0. So your first point on the graph would be at 0, 0. Can you have a negative amount of tickets?
No.
No. So you do not graph below the negative, below the x line or the y line, or past the y line. Then you can see here we plotted the ordered pairs. So 0, 0. So whenever you are dealing with a real life problem that you know can't be negative, you can draw your graph like this. It looks like the L, because you can't have negative numbers.
Oh yeah, makes sense. Those ones are way easier.
Yeah. Well, they're less to graph. So then we plug in each of our points. 0, 0, 1 and 15.95, 2 and 31.9, 3 and
You have to write the graph.
yes. However, you can do a simplified graph. Let me show you. I don't want to erase this yet, so I'm going to move my camera this way. Yep, I dropped it.
Why did I put parentheses?
Why or what?
Put parentheses.
All right, so this is I'm okay if you draw a graph like this, just because I just want you to understand the basic concept. Okay, so you have that, and we have, so this is obviously 0, 1, 2, 3, 4, 5, because we're only going to 4 tickets. And then you can put your dots like this. We know this one's at 1, 0, 0. The next dot is at 1 and 15.95. 2, we know it's a constant rate of change. Like that. So I don't mind if you do that. And then over here, you're going to put 15.95. What's the 2? 31.9.
Okay, that makes sense. So it's way easier.
It's like a little shortcut. I'm okay with that for your graph. Because normally you're not going to graph something quite this complicated. Oh, and then make sure you draw your line. Because the more tickets you buy, the more money you spend. Any questions on that? Excellent.
You're not moving on here, right?
All right, example 5. You're writing this in your journals. A cereal bar contains 130 calories. The number C of calories consumed is a function of the number B of bars eaten. So that's just what your X and Y's, they're just giving you different variables for your X and Y. So they're asking, does this situation represent a linear function? Find the domain of the function. Is it discrete or continuous? And then graph the function using its domain. So in this case, can you eat a part of a cereal bar?
Yes.
Yes. So we're going to have to call this what kind of continuous? It tells you that there's 130 calories per number of bars that you've eaten. So that would be your rate of change, correct? So 130B. So C equals 130B. So as B increases by 1, C increases by 130. So we do know it's a linear function.
Yes.
And then we did decide you can eat part of a cereal bar.
Cereal bars aren't that good. I don't know.
Most of them are not. So we know that it's anything greater than 0, because I took one bite of the cereal bar, decided it was gross. That means it's continuous.
What are the chances?
All right, so now we're going to plug in my computer, because it just told me I needed to plug it in. Thompson, will you go get my charger out of my backpack in my office? It's in the very, very front pocket. So you'd plug in these points. So if I ate no bars, how many calories did I eat? 0. If I ate one whole bar, how many calories did I eat?
I don't know.
130.
130 calories.
If I ate 2 bars,
260.
3, and 4 bars.
That's 20.
So I have made an input-output table, so I have some ordered pairs.
Can we just write the ordered pairs?
Yes.
The output table?
Yes.
Uh-huh.
But make sure you write the equation that I told you. Thank you. I need the block, too. I don't have a C charger right here. Sorry. Yes. Make sure you have the, what did we say it was? C equals?
C equals 130B.
Excellent job.
C equals 130B.
A little late, but I'll take it. Thank you so much for doing that.
How much did I miss?
Nothing. We talked about ordered pairs, which you know how to do. Did you write the example of the equation that I verbally said out loud?
C equals 130B.
Yeah, I wrote that.
That's what you need to do. And then you can just write the ordered pairs if you want. You don't have to write the whole table.
Charlie just said it again.
And then how would you plot them?
C, oh my.
I'm not going to make you graph them.
Okay, you would write like the first one, and then the last one, and then you do it. It could do a rate.
So it is, you draw the line. Oh, I messed up on the last graph. So the last graph was a discrete or continuous graph. It was discrete because you can't have a part of a CD, right? I made you draw a line. Can I draw a line if it's, you cannot. So erase that line because it can't, like here, it includes all the information between the dots because I can eat a part of a cereal bar. The CDs, you just have the dots.
So I'd erase the line.
Correct. Just have the dots. Yep, that's my bad. I get ahead of myself. So, but here, since I can eat a portion of a cereal bar, you do draw the line. So just make sure you understand that. So short version of this, if it's a discrete graph, it's just the dots, ordered pairs. If it's a continuous graph, you draw the line. Comprende?
Yeah.
So if I ate, for fun, if I ate 3.5 bars, about how many calories did I eat?
3.5 bars.
Hmm? You can give me an estimate.
Around
350. No, 480. 480.
No,
Yeah, 480.
450. No, 475. 475.
I would have said 450, halfway between 400 and 500.
230.
I said 450 at
330,
first, and then I
sorry.
just tried to follow Charlie.
No, but you're fine. Those are all good. Excellent estimations. All right. You do have monitoring progress, but we're going to go ahead and do the last example because we're out of time. So when you go back to your classroom, you need to make sure sometime between today and Monday you do all the way through number 12.
We're not going to move on?
No, tomorrow's Friday.
Okay. So we have myself?
No, you'll have a practice assignment. But remember, I don't grade any of this till Monday. So you could work on this tomorrow during class and then do the practice. As long as it's all done by Monday, you're fine. All right, so we're going to write a real-life problem to fit the data shown in each graph. Is the domain of each function discrete or continuous? So looking at A, discrete or continuous? Discrete, because it's just the dots. Is it a linear graph?
Yes.
Yes, it forms a line. It just doesn't have the line drawn, but it does have a constant rate of change. So what did we start with on this graph? 6 things, whatever it is. We started with 6 of them, and then each time something happened, how many did we get rid of? 1. So my rate of change is down 6 over 1. So you already know your M value, which is? Nope.
6.
Down 6. Make sure you have the negative, because we went down 6. Okay? And then your B value, where did we start?
6.
Oh, we didn't go down. You were right in the first time. It is 1. It's negative 1. We started at 6, because that's our y-intercept. And then our value of our rate of change is we went down 1 over 1, right? So then your M value is negative 1.
So would that be domain or what?
That's just your slope, your rate of change.
Slope is
So you could say y equals negative 1, write this down, x plus 6. Y equals negative 1x plus 6. So there's your slope-intercept form of this equation, correct? And then we know it's discrete. So it says write a real-life problem to fit that. So let's see what they give us. So they wrote the tables.
It would be discrete.
One, it goes down one.
Sure. That's disturbing, but okay. So, for example, in this one, you have two people bidding on 6 coins at an auction. Each coin is purchased by one of those two people because you can't buy part of a coin that goes down by 1 coin each time. You could say playing the marbles game, and each time I shoot a marble, I get a marble, so 1 less marble is on the table each time. You can't have a part of a marble, so that's discrete. Just any kind of example that talks about discrete, I would accept. You can say I was mad and I started breaking my CD collection because they were obsolete. So every minute that went by, I broke a CD.
I ate
That's so sad.
PB&J sandwiches.
I still have my CDs from high school.
So I say like
Every time I ate one.
every time I broke a pencil, I grasped it down.
Can you have part of a
The
pencil?
scale stirability
You can
went
kinda
down
have-
by one.
You
Every
can-
hour that went by.
No, because you can have part of an hour.
Every time
It needs to be an object that you got rid of.
Every time the sunset.
You can have part of a.
Every time I ate
Every
a PB&J
stripe on the American flag.
sandwich.
Okay, but it doesn't start at 6. There's 13 of those.
Every door I shut.
So we didn't
Every door I shut.
Why don't you just write down the example it gives you?
Every door I had.
There's 6 coins for sale. Every time one is purchased, there's
Every
less.
door I had.
All right, go to the next one.
I eat
Real life problem to fit the data shown on the graph. Is this domain discrete or continuous? Hello.
Continuous.
Thank you.
Because it has a line.
Because it has a line and it can be anything in between here. So there's 2 possible variables of x and y. Notice that the sum of the variables is always 6. We already determined that was the equation. So it can be any real number between 0 and 6. It could be 1.5. Well, it's not infinite because it's 0 to 6. But any real number in between 0 and 6 would count. It's not infinite. It's all real numbers between 0 and 6. Infinite means all real numbers. In this case, it's all real numbers specifically between 0 and 6, including 0 and 6. So here's another one. They're bidding at another auction for 6 ounces of gold dust. Can you have part of 6 ounces of gold dust? Yeah, I could buy 3 and you could buy 3. Okay, so that's an example. All right, so make sure you do your monitoring progress before Monday. Have a good day.
That'll be good.